thank you so much for joining us today and supporting the DMS debates. Very much appreciated that you all can join us today. As you know, we do these quite often in DMS. We bring people together. It's a community after all. Today, the concept is taking the pros and cons of a very interesting subject. Welcome in our teams. Just to give you a little brief background, we have Mr. Mahmoud Al-Alfi from ADCO, who's going to be our very respected moderator. Okay. On the team, speaking in favour of the motion, we have Mr. Orlando de Matos of Gasco, Mr. Willem Arntz of Tebedin, and Mr. Prakash Kumar of Composite Pipes. Thank you. Speaking against the motion, we have Mr. Hussam Sabri and Mr. Winston Renaud. Unfortunately, one more speaker who is due to join us today at the very last minute had to cancel. So it's okay, we make do and we enjoy the debate. One of the most important things, if we can just remind you, we have a voting form, feedback form. What we do in DMS with our debates really relies a lot on you. It's your feedback that helps us create these motions.
Good morning, ladies and gentlemen. Assalamu alaikum wa rahmatullah. I would like to thank the sponsor as well and the DMS for hosting this event. And my role will be independent, completely not biased. So I will just would like to highlight the fact that at the early stages of last decade, when oil and gas industry was erupted, the industry depends mainly on steel and steel grades as a material of construction for all process equipment and facilities. And the different grades have been developed, starting from normal carbon steel to stainless steel and even with high chromium alloy. Then it retaliates to or erupted more into corrosion-resistant material, RCA, ink alloy, and molybdenum, and other alloys that will give high corrosion resistance and high abrasion resistance. And the dependency on the metallic material for construction of the different facilities was there until the time comes and the non-metallic industry started to evolve, the plastic industry, and with the technology, the plastic industry started to produce heavy duty and industrial grades that started to take a place and started to in certain application, like in cooling water application or closed drains. Later on, the technology has retaliated to have heavy duty application in surface and even on subsurface in tubulars as well. So today we have two teams. One team is led by Mr. Orlando from Gasco. He is going to deliver his presentation in favor. And one team is led by Mr. Hussam Din Sabri from ADGAS.
Assalamu alaikum. Good morning, ladies and gentlemen. I'm just going to give a brief presentation for the motion. So, as you know, the motion is non-metallic piping is more advantageous than metallic piping for fire water and cooling water systems in hydrocarbon processing plants. Glass reinforced plastics, as you can see in this table, are widely used for different services in oil and gas industries, petrochemicals, refineries, desalination, and water treatment plants. You also can see some fire water networks, cooling water systems, even crude oil transmission lines, oily water, chemical injection are using very successful and are among other systems that are in the table and that are using this glass reinforced plastics very successfully in all these petrochemical, oil and gas, and refineries industries. Advantages of GRP. So it is a durable and corrosion resistant. So is inert to internal corrosion from chemicals, crude oil, residues, injection water, and bacteria. Similarly, with regard to external corrosion, they are very resistant even in very aggressive environments. So cathodic protection also is not required. In terms of weight, they are lightweight and very easy to install, so without the need to heavy equipment. So the installation of glass fiber reinforced plastic pipeline systems are typically 80% of the cost of the carbon steel. The resistance to corrosion and UV light reduces the maintenance costs for both above ground and buried pipelines. And in terms of energy, so also the smooth internal surface reduces the head loss, resulting in lower pump energy consumption. Raw materials. Glass fibers and resins are the major components. Fiberglass pipe uses only thermosetting resins cured by heat or chemical additives. Once cured, a thermoset is infusible. It means that it cannot be remelted and is insoluble. There are three main categories of resin. So you have epoxy resin, you have GRE, you have polyester resin, GRP, and you have vinyl ester resin, GRV. The GRP materials are made of three layers. So the inner coat, which gives resistance from corrosion, middle structural layer, which gives structural strength, and the top coat, outer top coat for UV protection. In terms of the design and manufacturing, so piping systems are designed and manufactured in accordance with international codes and standards as ISO 14692, DEP, and other standards like ASTM standards. Both give recommendations from the qualification and manufacture, design, fabrication, installation, and operation of glass fiber reinforced plastic piping systems in offshore and onshore. So pipings are manufactured by filament winding of continuous fiberglass roving impregnated and saturated with resin. The jointing systems. So the more common jointing systems are indicated in this slide. So you have the adhesive bonded joints, laminated joints, mechanical O-ring, flanged joints, threaded joints, and the interface between metallic and GRP. The type of joints also is specified according to the diameter and design pressure. So from 15 to 600 millimeters diameter and design pressure between 40 and 65, the main common joint used is the adhesive bonded joints. Between 700 and 1400 millimeters and design pressures from 10 to 25 bar, the mostly common used is the lamination. From 50 to 200 millimeters, design pressure from 100 to 120 bar, the common type is threaded joint. And the diameter from 100 to 300 millimeters and the design pressure from 20 to 25 bar, the K-lock is mostly used. Of course, the fabrication of these GRP materials can go up to 2600 millimeters, for which the design pressure and the jointing system needs to be specified. I would like to draw your attention for the following point. So, our experience with GRP pipe systems show that most problems are joint leakages, which are mainly caused by inadequate system design and installation, like poor workmanship. GRP, therefore, requires more attention and guidance than the installation of the carbon steel. And this cannot be captured only in the standards like ISO, DEP or DGS, but requires well-trained personnel, good workmanship, certification of joiners and supervisors. We cannot blame the GRE, so if we don't take in attention these points. Root cause analysis, in general, they reveal non-conformance in the installation of the GRP piping with respect to design documents, construction drawings, QA/QC, hydrostatic test reports, in addition to the non-compliance of design requirements by some contractors, qualification, certification requirements of supervision, and materials quality in the projects, they emerge as major gaps. To overcome these issues, we think that a single point responsibility should be specified for GRP pipe installation projects. The manufacturer of the GRP system shall be, among others, to carry out the system design, the product qualification and supply, supervision and installation, and the supervision of system hydrotesting. Other points of attention are to select a pipeline manufacturer or installation contractor with proven records in this field, of course. He has to prove that where did he work, what is the feedback from the installation. Also, certification of joiners and supervisors is of the key importance. Apply clear working procedures for handling, storage, installation, and joining of piping components. Supervision and QA/QC during both manufacturing and construction phases. And also a good UV stabilization package is needed to avoid UV degradation, storage, and above-ground piping. Okay. So transport and storage is also very important. Are we asking anything here that is not also requested for carbon steel? I don't think so. But why we don't ask, why we don't go through this one? Because it's GRE. So for carbon steel, we have PQRs, WPS, welder certificates. Welders, they are certified. For GRE, assembling, is it certified? Supervision? These are major issues. Other recommendations are part of the installer qualification competency check shall be a 100,000-hour survival test of test spools prepared under simulated field conditions, are fit for purpose and are capable to meet minimum design requirements, similar to the carbon steel. You cannot do any welding without preparation of PQR and WPS. But are we doing for GRE? The manufacturer also shall provide a detailed checklist for quality control steps for the field assembly of all joints involved in the GRP system. This checklist shall include instructions for inspection of joints, specifying recommended timing of inspection after joint makeup, the method of inspection, data to be recorded, and acceptance criteria. What are we doing for carbon steel? We approve ITPs, inspection and test plans, detailed ITPs. Are we doing the same for GRE or for GRP piping systems? All joints, of course, shall be included in a joint map with identification of the joiner, GRP material markings, joining system, atmospheric humidity and temperature, the adhesive kits, each one resin and hardener, identified with production batches. We have the welding map, where we can trace the welder. Are we doing the same for the GRP piping systems? So having a similar jointing map where we have the joiners identified, material, the batches for the resin and hardener. This is a question. So based on the full hydraulic transient or surge analysis performed, the contractor shall provide pressure damping arrangement, surge pressure control system, overpressure protection at identified locations in the fire water systems to limit the risk of water hammering. So in conclusion, we have only 12 minutes. So GRP is an excellent option and has been used worldwide with great success in oil and gas, petrochemical refineries, desalination, and water treatment industries. The installation cost of GRP pipeline systems are typically 80% of the costs of carbon steel, with very low maintenance costs during its lifetime. Design, qualification, manufacturing, installation, as per the standards, and single-point responsibility involving manufacturers throughout the process life cycle are the key of the success. And with this slide, I finish this brief presentation. Thank you.
Mr. Orlando, you still have 3 minutes. Okay, so in case that any of your team would like to add comments, is very much welcome.
Thank you very much, Mr. Orlando. This was very useful. I would like to add a few things of my historical experience of GRP pipes in the Emirates. As consultant, in fact, you have to advise your client what is the best material to be used for certain purposes. Track record of a certain material, you can say, okay, client, this is a proven track record, no failure, very well performed over the last years, or over a number of years, and use this material. So what happened, in fact, is that in '94, we had a problem. Vertel had a problem, Vertel Ruiz had a problem with Bona pipes. And Bona pipes, for people who don't know this is a corrugated steel core, in fact, and on both sides you have a kind of cement lining with reinforcement. In Vertel, these pipes were installed in the early 80s when the plant was built, and all these Bona pipes supplying seawater to the plant were in fact corroded, holes were visible and not anymore in use. So at that time, we were involved and awarded by Vertel to provide, in a very short period, because a plant shutdown is disastrous, of course, a new water supply pipeline. Now, the new water supply pipeline couldn't be buried, should be above ground, and should have a diameter of 2 meters. At that time, GRP was hardly available in this particular diameter, but due to efforts of the manufacturer, the stress calculations were carried out, and which was not easy for an above-ground pipe, GRP. And finally, the water supply line was built with a lot of restraints a lot of foundations, straps around it, etc., etc. Now, I called, of course, participating in this seminar virtual a couple of days ago, and I spoke with the management there, and I said, what is the situation with this line, which we temporarily built in '94? And they said, well, our last maintenance was a couple of weeks ago. We went inside the pipe, and it was like new. So that is the reason why I'm sitting here in favor of plastic pipes. Thank you.
If we have 1 minute more, do we or no?
You have 1 more minute, but I thought that we'll give the floor to Mr. Prakash.
Exactly, yes. It's to give the floor to Mr. Prakash.
Yes, please.
Because I do believe that the involvement of the manufacturer in the project, from the project lifetime, is the key for the success of the system. But you...
Thank you very much. In addition of that, we have one more success story. Actually, 2 years back, we have done one R&D for the existing pipe that has supplied in 1981 or 1985 something in the PDO site. And the integrated team was very much worried about the design life because it was crossing the 30 year of the design life. So what Shell has done, Shell has just cut the piece of pipe, and they have done some R&D on those pipe. And we have done the several qualification tests, and we conclude that the design life of those pipe can be extended next 30 years. So it will be almost the new pipe. So that will be also one of the success story for the GRE pipe. Thank you very much.
Okay. So thank you very much for Mr. Orlando's team for Pro. Now we'll leave the floor to Mr. Hussam to speak against.
Good morning, ladies and gentlemen. First of all, it's always great to be here. I mean, among friends and colleagues. And it's always a great pleasure to share, the experience. It's all about sharing knowledge and experience. And there is a key message first for our rivals. It's easier said than done. Huh? That's the key message about applying GRP. The second thing I would like to confess about something. Myself and Winston are fanatics about GRP. And because we've worked, with GRP systems for a long time, we think we know its weaknesses. Yeah? So we'll go, through it. Right. Till this is sorted out, we have limited time. So first of all, as an engineer, I used to specify materials for cooling water systems, fire water systems. And I think all the materials engineers in the room would agree with me that the most techno-economic material for cooling water and fire water is GRP. Right? Agreement? So we have fanatics about GRP as well in the room. However, how many operating companies or users were bitten by GRP failures? I think a lot. We've seen lots of failures from a user's perspective. So for plants and plant managers, if they have failures with GRP, so why do we insist having GRP? So this adds to the problem itself. So get rid of GRP. Let's use metallic materials. We know metallics. We've been using it for ages. And it's less problematic than GRPs or non-metallics. So again, the key message was non-metallics is the best material, techno-economically. It's the most suitable material. It doesn't corrode. Its lifetime can go forever. It has less problems. However, we've had lots of failures, so many failures, and some of them were catastrophic. Soil washing, equipment collapsing, so it adds to the problem. So let's shed light on these failures, why it happened. And in case we cannot avoid these, the key message would be to use the metallic material, which all of us are familiar with. Although I don't like this, of course, to happen, but anyway. So first of all, we need to ensure before using GRP or FRP in fire water systems that it is suitable in terms of the zone, the fire zone itself, in terms of pool fire or in terms of jet fire. So once this is cleared, then we need to understand how inspections can be done during the service, during the lifetime of the GRP. And when can GRP more economic? So the life cycle cost is the one which we calculate for material selection is very important. I mean, if we have a relatively short lifetime, then metallic may be more economic. Relatively short lifetime, I mean like 3 years. But if we have something like 20 years or 30 years, then GRP is definitely the solution. The operational limits of GRP needs to be ensured. Currently, the technology has limits in terms of use of GRP, and the user needs to specify, I mean, the usage of GRP versus the limits, the operating limits and the design limits that we have. What are the QA/QC that can be done during design and manufacturing? This is a key issue for GRP versus metallics. Because GRP design is a very critical exercise. Design of GRP as a system. Till today, it's left in the hands of the contractors, GRP contractors or suppliers. So they design the system. It's relatively a black box. So standardization needs to improve on this part. We need to ensure that the design of GRP is done adequately. Most of the failures of, let me put it that way, most of the failures of GRP are because of design issues, manufacturing issues, and installation issues. If you successfully design and install, manufacture and install a GRP system, it will work forever. It will have no problems whatsoever. So, Winston, how can we introduce a quality item or element in the design, GRP design?
Probably the best way is an independent check. It's just like when I do work, I try to have one of my other engineers take a look at it, and they're fresh and they're coming in clean. It's the same way. If we can have an independent resource to look at the product and oftentimes do an independent stress analysis. Oftentimes that's completely different because many of the people who do the design and stress analysis of these products are not particularly composites-oriented people. So if we can come in with a pure composites means of stress analysis, ply for ply, looking at this, we can end up with another strategy that sometimes will unlock the door to insights that are really valuable. And we can all get together and agree. And amongst gentlemen, we come up with a good design, but it's the idea of the power of diversity.
What about standards? I mean, how is it progressing now with ASME and...
Yeah. It's interesting, there's a new pipe standard coming out of ASME. We're kind of participating in the final stages out of, ASME in the United States. And it is kind of akin to the ASME B31.3. In essence, it's a traditional stress analysis design strategy. And the thing I try to explain to our people and our clients, which are the Exxon Mobils and the Shells and the Chevrons of the world, is that we can't accept the standards lock, stock, and barrel like we were talking earlier about AWWA M45. And there's parts of that are absolutely excellent. The hoop analysis, impeccable. The longitudinal analysis is absolutely wrong. And it leads you to believe the longitudinal stresses are not a factor. We can have design stresses in the longitudinal direction are very, very low. And in actuality, if you do a thorough axial stress analysis, I'm only picking this for one example, what you find is the axial strength of the pipe has to be vastly bigger than it typically is. And just an example, we've got to be careful of the standards. Part of them are good, some of them aren't particularly good. We've got to be able to do something fresh. I'm just winding down here. Do something fresh so there's a diversity where different people are looking at the same thing from different angles. And I might not see something that my coworker or my partner in the manufacturing business does. I might see something that he doesn't see. But together, when we've come fresh several different directions, and particularly emphasize the pure composite analysis strategy, the chances are, if there's something wrong, we'll see it.
All right, thank you, Winston. So the key message is codes and standards, they don't really cover the design of GRP in a similar manner like metallics. So this is a key point. The second, the design needs to be verified, maybe by a third party, who can really review the design of a GRP contractor. Soil properties is a very important factor, and we've seen lots of failures in GRP systems that were actually due to soil-bearing capacity not taken into account. So the entire GRP system collapses, unlike metallics, which can provide flexibility in its design and its strength, let me put it that way. So GRP is again sensitive to soil properties in cases of burial. Manufacturing is another important element. Manufacturing involves raw material. The manufacturing itself, the manufacturing procedure itself, or the manufacturing process itself is a very important thing. I mean, quality of reinforcement, like e-glass, which type, resin, the quality of resin itself, the grade of the resin, winding angle, proper QA/QC must be applied. And I think, Winston, you have a lot to do with this, like checking the quality of manufacturing of GRP systems. Can you elaborate on this?
Yeah, the shop work is typically considered taken for granted. And we have a project, a failure in Sabik Yambu olefins, where the pipe looked fine, but when you got into and there was little to no quality management done on it, so the owner just assumed it's going to be fine, and the alligators came roaring through the fence. The pipe was way under strength, particularly in the longitudinal direction. And when you got into it, you found the void content, sizing and binder problems, cure problems, and you ended up with a pipe that was maybe half the strength it should have been, particularly in the longitudinal direction. So you had a lot of the circumference cracking, and the end-to-end pipe was useless. It's being completely, it's like chemia base plant where there was no saving any part of the system. It was completely replaced based on some good financial analysis. So just because you have a pipe doesn't mean it's particularly suitable for service. And actually testing it to be able to evaluate the physical properties is pretty tricky.
All right, Winston, sorry for interruption. Another question. Now we installed the system and it's working fine. How can we inspect it during service?
Okay, that's another good one. I happen to have some literature here about at least the things that we're trying to do in terms of we not only work on new systems to get the control risk from here to here, we try to take existing operating systems and do the same thing.
Because, you know, the key point, I mean, a key argument using metallics or the people favoring metallics is that we can inspect it, you know. Right. We can do any NDT that we need to.
Right. You know, on the list I gave
the integrity of metallics. What about non-metallics? How can we inspect it in service? Is it just visual?
Yeah, in many ways, it's actually more friendly than metallics because for the most part, these non-metallic materials, at least for some distance into the wall, are transparent. So we don't particularly need X-ray. We can do our eyes, and an awful lot of the failures that are happening outside of bonded joints will be on the outside of the inside surface. So if we can inspect on the inside, so using ROVs, various and sundry internal inspection techniques. Another one is if we have failures and very careful failure investigation. We had in Oman a major series of 8 failures. And in real careful investigation of those 8 failures, we really got an understanding of the nature of the system and where the system was going in the long term. So looking at failures, looking at inspections on the inside with various type of push cameras or remote operated vehicles, thermography, microwave, a number of different techniques can be used to start gathering. Once you have an operating system, you have a real black box. And there are a number of techniques we can still use by monitoring failures, by doing inspection, to be able to understand if the system is in distress. If it is in distress, what can we do to intervene in the mechanics of failure?
Okay, thank you, Winston. One thing to take into account again, GRP, once it fails usually from a joint in many cases, in most of the cases. And when it fails catastrophically. So it bursts or it snaps. So the amount of water gushing out can really wash out the soil, leading to catastrophic failures. This is one thing that can be taken into account. I mean, for metallics, it's better for metallics. Metallics will, I mean, if it's cement lined, cement will collapse first, and then it will progress as a localized failure. Failure usually is non-catastrophic in case of cement lined piping. But again, metallic has other issues. I'm not going to speak about problems with metallics. The chemical resistance needs to be ensured. If you are using GRP for a service other than seawater, the final thing is majority of GRP failures are related to installation. Mainly cleanliness of joints, improper installation techniques. So what's the role of QA/QC during installation, Winston?
Yeah, that's... You're exactly correct. We typically think of installation being about 50% of the causation of failure. And what you find is that with glue joints, when they're small, they're relatively easy to do, but with larger glue joints, they're really tricky to do well. I mean, it goes up exponentially as far as the difficulty as your pipe gets over about 12 to 18 inches. With laminated joints, actually, where the glue joints are oftentimes the weakest spot in the pipe wall, the bolt pipe wall is stronger than the joint, particularly in bending and also axial tension. When you look at a laminated joint, it's usually the strongest spot. If the secondary overlay material, that's the bandage you're going to wrap on the outside of the thing, sticks to the basic pipe substrate that are butted together. And that's not difficult. We've, in large diameter pipe, in our experiences, tens of thousands of big diameter joints, we've never had one leak in hydrotest. And there's never been a leak in later failure. Although in some systems that we've been involved in failure investigation, 20% of the joints are failing. So it's not a give me. On the other hand, it is doable. We can do it in such a way as to have an extraordinarily high success rate.
Mm-hmm. Thank you so much, Winston. So, I mean, as a closing, or to summarize what we've said, GRPs fail usually during design, manufacturing, and installation. If you cannot really avoid what we've just said about introducing quality during the design, during manufacturing and installation, go for metallics. That's the key issue. Introduce an element of quality. So as a user, from a user perspective, we are coming up with standard operating procedures that covers the stages or the lifetime of GRP. In terms of design, in terms of manufacturing, installation, and even during service, what to do. How to do the checks, how to do the QA/QC is a very important factor towards the success of GRP. If you cannot do that, go for metallics. I hope I tried today to be a devil's advocate. Yeah, thank you so much. Thanks.
Thank you very much, Hussam and Winston. I believe Winston should leave Hussam and join the other party because because you were defending the non-metallics. Okay, so as for me, the lesson learned and the outcome of this debate, I have just put some bullet points. First, in order to decide whether to go for metallic and non-metallic, we have to be very clear about design specification. And as per the design specification, like fluid characteristics and design conditions, pressures, temperatures, then we have three options: either to go for carbon steel with the different grades, or for corrosion-resistant materials, or for non-metallic. And non-metallic, we have ranges, not only GRE, we have RTP, we have different types of non-metallic. So we have to be very clear about design specifications, and based on the design specifications, if we have both material of construction can be used, then we have to go for the life cycle cost analysis. It depends on what is the design philosophy, design options, whether the installations that is desired to operate for 20 years or more. Then we have to apply this life cycle cost analysis in order to select the most appropriate material of construction. On the other hand, we have to ensure the quality of the material. So like, for instance, when we design a plant, and we have to go and conduct audits on the steel mill in order to ensure that the steel which will be utilized for construction of different facilities, pipelines, pressure vessels or so, that it is of the acceptable grade. So the same can be applied for the non-metallic vendors and manufacturers, where we need to go and we need to formalize an inspection scope of work, TOR, and an audit in order to ensure that the vendors is producing an acceptable industrial brand, and it's not only a commercial type, which can lead into future failures. The third bullet point is the QA/QC. It is very important that we have to ensure that the material, the non-metallic material during construction phase and during installation phase as well will be controlled and monitored in order to ensure proper design, manufacturing, and installation. Vendor selection is a very important aspect, and which we need to put also a specification for the vendor selection, because we have seen quite a few number of vendors that they claim that they are manufacturing a suitable heavy-duty brands or industrial brands, which we discover later on after utilization that it is not meeting or it's not meeting our expectations. There is also a responsibility on the vendors, the technology improvement, R&D. So we know that we have shortfalls, for instance, in the jointing, the jointing material and the joints itself, pipe joints. Then we have to invest more in improving this technology. Also, we have a limitation in terms of the utilization of non-metallic for high temperatures, and which limit the utilization. Like, for instance, that we are talking about fire water, and cooling water. Okay, why we don't expand for the hydrocarbon services? Okay, why that we don't expand the utilization in critical areas, which requires fire resistance. So we need to invest time and effort and money in order to improve the technology. Also, we need to work out on identifying the different failure mechanisms, because the failure mechanism of the stainless steel is very well controlled by API, and based on that we can identify the inspection scope and the inspection technology required. The same should be applied on the non-metallic as well, so that for different application there is expected failure mechanism, and based on that we can say, all right, gentlemen, this kind of inspection scope will be applied for this kind of services, so that we ensure that we are not taken by surprises by sudden failures or leaks. Last but not least, from integrity point of view, okay, for the metallic, we can identify the remnant life. How long the metallic pipeline will safely operate. Okay, for the non-metallic, it is a bit difficult. So for the committees that set standards and like ISOs, we need to think about a mechanism whereby we can estimate the remnant life, so that the operator can have an assurance that this kind of non-metallic will live for that much period. Okay, so now I will leave the floor to our esteemed audience to address their questions and queries.
Thank you very much. Actually, I would like to thank both speakers who are actually with metallic and also with non-metallic. And what I understand actually from both of them, the precaution which should be needed to be taken care for both is, I can say, same. What I can see, the main thing or the main issue in using actually non-metallic is the design. And everybody is feel comfortable, because metallic, it's been known long time ago. the designer, the consultant, everybody, he feel comfortable, to design a metallic without bearing mind for the cost. Because they used to design. The utility people, they bear the cost. And what I understand from Mr. Orlando, from his experience, is 80% less for non-metallic. So this should be taken care. Now, we have to be outside of the box. We have to get a designer, an engineer to design. Why we keep this only to the manufacturer? For non-metallic, we have a designer, we have a companies who design for the utilities to supervise. Now, this being kept for non-metallic, but we don't have to blame the non-metallic manufacturer. We have actually to go and to use non-metallic. We don't have to be afraid. From what I have seen and what I understand from also Mr. Orlando presentation, non-metallic GRB, it's promising. Especially now we are facing a problem from the economical point of view. The main thing, with what Mr. Hassan mentioned, it has, when it is breakdown, we lose a lot of water during the breakdown. That's also with DI pipes. When it is due, sometimes if there is a surge hammering in the system, 600 pipeline broke and then split from the flanges, or it's split from male and female, both pipes split. We lose same quantity of water under the pressure, maybe 14 bar pressure, something like that. So the loss, it's same. I think we have now to get a consultant engineering who design the GRP pipe. But I understand also, I was talking with my colleague, Dr. Salim, that now also GRP, they could absorb, the traffic, they could absorb the weight. Now, almost in the future, I can say it's similar. But in GRB, especially if in the corrosive soil, it's the best. Also in the metallic, we have to be very careful with the lining, with the protection from corrosion, either cement, mortar lining, or epoxy coating, or polyethylene sleeves, or whatever. So that's also we have to take care. During the laying and installation, same thing. We have to have a proper bedding. We have to have a sober, a better backfilling. All of this supervision should be taken care, even in metallic, not all non-metallic. So what I feel, from my view, that non-metallic GRB is a promising. It is very good from the economical point of view. Only the main thing, we don't have a company, consultants to design that for us and to supervise for the utility. Thank you very much.
Yeah, I think you are absolutely right. The example what I've given to you for the fertile seawater supply line in '94, that was a challenge for our company. We had some expertise from a very specialized company at that time. We used a sophisticated computer program, CSR2, and we used, in fact, because it is a composite material, we used special properties of the line. Now, it is, of course, always the consultant's, let's say, responsibility to design the pipeline system. Not only, of course, a composite pipeline, but also metallic pipeline. But you have to go, as owner of a plant or a system, you have to go to a specialized, reputable consultant who has a track record in designing GRP pipelines. Because if you go to somebody who is just doing some pipeline systems, metallic pipeline systems or water pipeline systems, and do not have this experience, then yeah, you will have failures. Now for GRP pipelines, you need far more anchor blocks. You need to see if it is above ground or below ground. You need a number of, let's say, values to be taken into account, which are different from metallic. So it is, of course, of prime importance to select the right consultant for this job with a proven track record.
I think there is a lot to be added in terms of codes and standards. For instance, if you compare the articles for metallic piping design, B31.3 for instance, versus the ones non-metallic, see the difference. If we refer to the American Water Works Association, like what Winston has mentioned earlier, it gives you, it's really debatable. I mean, the articles under AWWA in terms of GRP design is terrible. So I think there is a lot to be done on the code side. Maybe the industrial committees need to do a lot. I mean, till GRP is being reviewed by the mechanical engineers in the respective departments of the user's side, then it will be a problem. If we cannot put like standards, clear standards to design GRP, then it's a problem. Then we will have to seek the help of a third party, someone who's specialized. But even though the team in the user will not have like the buy-in, the comfort to use it, they will not be able to review it. If you don't have a clear code, a clear standard, like API, for instance, inspection, for instance, then it's a problem. So there is a lot to be added on the standards and code side.
Thank you very much, Sam. Okay, the second question, please.
Good afternoon. My name is Shyam Pandey. I am from Alosan Gas. We are the recent commission plant which is used, I think, the maximum GRE pipings and equipment in our plant, lengthwise and quantity-wise. I just say few things also to support of non-metallic materials. Just for example, I'm basically a metallurgical engineer. I graduated in 1981. My department was metallurgy engineering, and recently same department has changed to material and material science engineering. And it is dealing 50% non-metallic is composites. So composite is the future. Let us not be afraid that these problems are not there. Since we have installed the composite material in our plant, and we got a lot of failures, Vincent knows also about this, but this is not any time I never hesitate to use in future product also. We have tested a lot of pipes, including Mr. Vincent's laboratory also. We have not found a single pipe which is deviating from manufacturing standards. So we tested also, there is no question of quality control at manufacturing stage. Yeah, I have not seen also. Just to give a number, I'll just share with you also. We got about more than 50 failures in our plant, and out of 50 failures, only 3 are related to joint failures and all. Remaining 47 are due to the people are walking on this, people are traveling on this, road rollers, a lot of equipment, construction equipment are passing on this, forklift impact, those are the reasons. So where the quality control will come? It is basically housekeeping. So this is my personal experience, and I fully support GRE is the future. We must go for that.
There are ISO 14692 part 3 is there, which is fully complying the GRP design basis. So if you are meeting the requirement of the ISO 14692 part 3, as well as the DEP and AWA M45, then I don't think design-wise we have any problem.
I think the new standard that's coming out for pipe, like I said, it's more akin to B31.3, which, I came out of the aerospace community. The art of stress analysis is pretty well established worldwide. And I don't care whether you're analyzing part of an aircraft engine, a wing, a boat, a piece of machinery for a car, a reinforced plastic pipe. The basic strategies are quite common in terms of understanding the material in detail, understanding the stress state, and try to mesh them up to see if we believe that for all the load cases, the stresses will be within an acceptable envelope. 14692 is a really awkward and convoluted standard. It really is more of a pardon? That's a polite word. Yeah, the Shell people that worked in the involvement of it originally in the United States were referring to it as basically an attachment or a reference to a specification. And the strategy that we've done with Exxon, we're just finishing a worldwide specification. We did Royal Commission, AdGas, a bunch of Shell eggs in the United States, engineering guidelines and standards. what we found is that the only way we could really end up with a document that was usable and functional is a very insightful specification that was created by the people who have to use it. The engineers that are going to enforce it need to be the ones that create it. So it is actually simple, straight to the point. Some standards might have 4 pages. The specification will have a half a page, and we'll say it more clearly and in a more usable fashion. We've got to make documents that are usable. They've got to cover the technologies. There's a good set of reasons why things fail, whether it's an aircraft, and I came out of Boeing and we were worried about engines. We had a pretty good understanding of that list of things that pretty was all-inclusive of why an engine failed, and in the design, construction, and maintenance operations of that engine, we made sure that none of those reasons for failure existed. If there is no reason for failure, guess what? It doesn't fail. The same with reinforced plastics. You find there's a very finite group of reasons why failures occur. And in risk management in the original project, we assist the Exxon teams and the SABIC teams and so on, make sure that none of those things exist in their system. Again, there is no reason for failure. The systems don't fail. In dozens of past recent projects, mega projects, if that kind of a strategy is applied, there's never been a failure. It's never happened. It doesn't exist. But it's common, like I say, that's a common thing to use in the auto industry, the aircraft industry. We're using basic risk management principles that, before they even thought about reinforced plastics, were well established and work very well. And now it's a question of developing the art, because composite technology is way different than metals. I started out in metals. It's interesting how much of our engineering community, the whole way of thinking and standardizing is unique to metals and very awkward to non-metallics. So we talk about standards. In the aerospace community, they're struggling. They've been struggling for 40, 50, 60 years to develop, since World War II, good standards for aerospace composites. In the piping industry, it's been the same thing, or in the tank, RTP1, ASME RTP1. That's a good document.
Since you are in the industry for many years, providing that you take all the measurement needed for the installation and manufacturing of the GRE or the composite, I would like to know from you guys the number of failure reported from the clients to you guys, approximately, along the years with different installation of the GRE material for different surfaces. I'm sure that you have done it for other than the fire water network or seawater networks, even for the hydrocarbons. And for a lengthy meters or kilometers of installation. And I'm sure also you do not only the manufacturing, but also supervising the installation itself, whether with you guys or with the third-party inspectors.
So wherever we are sending the pipes and fittings, we always recommend to do the construction work by ourselves only. So this will ensure that the integrity of the pipeline system during the installation.
I would like also to share our experience in GASCO. We have different plants commissioned at different times. 1984, 1996, 2001, 2010, and 2013. 1984, almost no failures. 1996, no failures, or almost very insignificant failures. 2001, not the same, no failures. 2010, option 4 project, a lot of failures and catastrophic failures. 2013, option 5, some failures. So my question is, why in the past, where the materials maybe not so developed, they are not failing, and now are failing? And for example, I can share also, in option 5 project, commissioned in 2013, we had a significant failure. That is a tie-in from the old line. So the old line did not fail, the new line is failing. And also to talk, to share with Osan, okay, of course, so anything fails, I understand that. And carbon steel, they fail. So why do we have RBI? How much effort and how much are we spending for implementing the inspection in order to have the proactive actions before it fails? What are we doing with GRE? Are we doing the same? I don't have any PM for GRE. I do nothing. I just remember that I have GRE in the plant if it fails, or GRP in the plant if it fails. So, I mean, so in conclusion, if we put all the efforts, like it was already mentioned here, in the design stage, also involving manufacturer, like Mr. Prakash also mentioned, during the project lifetime, there will be accountability, and we believe that is a key of success for any GRP installation. In option complex, the failures are mainly associated to the latest projects, 2010 and 2015. And the failures are associated to design, material traceability is not there, the qualification of joiners do not exist, and this is what we notice. So wrong design, normally the hydrant, so there is a big concrete on the top, and in these locations we have some failures, which is a design failure. So the joints, metallic and non-metallic, should be up above the ground, so, and protected. I mean, so basically what I want to say is that the failures are associated to the design. So maybe in other plants we have different failures for different reasons, but in option is like this. For example, Bab plant commissioned in 1980. What we did, we replaced the carbon steel piping by GRE in the same trench. Is it correct? It fails. Okay. What is the reason? Project. So, I mean, so we have to be clear on that. So that's basically what I want to share with you.
I just want to elaborate a little bit more what Mr. Orlando has said and what this gentleman from Al Hassan also said.
Can you please state your name and your company?
Sorry, my name is Abdel Haq. I am from GASCO, the engineering division, and in GASCO. So I know about the problems in Habshan in our plants. So my point of view is that when we decide to reject the GRE material because of failure, we have first to investigate and to know what is the reason for that failure. I will not reject the material if it is well designed, if the manufacturer is okay, if the contractor is okay. Then if I have failure, I can reject. But if I know as per the root cause that the design is wrong, the manufacturer is lousy or not qualified, and the contractor also is not in that business, he treats GRE like carbon steel, then it's good ground for rejection. From my experience in GASCO, the failure which we have happened in our plants, I am 15 years in GASCO, and in one of our plants, it was like similar to BAB. It was carbon steel changed to GRE. When we started that job, that was a fit stage, then it was transferred to project. This project, when it was taken, they handled it like carbon steel. They awarded job to a contractor who's not in the business of GRE. The manufacturer was not good quality. And to tell you the truth, I was suspecting something will happen at my lower level because I didn't like it. I thought GRE is like, between quote, noble material. You should treat it like a baby. So take care, do good design. Now regarding design, also we have noticed that in the past 10 years ago or before, the stress analysis was done in this plant, which is Buhasa, based on ASME. B313. It should not. It should have been as per BS, or now it's ISO, that number 1402. So I would be convinced to reject GRE if I do good design, proper selection material, proper quality, then I reject. So this is how we should make a decision. once you retest, etc., it should not have any more problem. It's the opposite of carbon steel. Carbon steel, after commissioning, you have no problem. Maybe after 5 years, you start having problems, etc. And this has to be really controlled, you know. So we should not reject the material just because we have failure. The only caution, it's this catastrophic failure, which should sometimes give some bad, you know.
What I would like to point out that earlier presentations recommended to go for a single point responsibility. It is to be given to manufacturer. But in a big project, it is quite difficult making GRP manufacturer as responsible for the whole installation, because the GRP pipe can have problems from the hydraulic design, installation, construction, manufacturing, from anywhere. So how is that practical to make GRE manufacturer responsible for the whole issue, especially GRP piping is scattered all over the plant. Unlike you have a compressor package, you can define the battery limit, it's easy. But how you can do that for GRP pipe?
Normally what we used to do it based on the specification. First we will, as a manufacturer, we always recommend to design by the manufacturer only as a consultant. And then we will supply and we will do the QA/QC. As well as for the site installation, we are sending our people who can do the jointing work as well as the supervision of the pipeline. So by this way, we can reduce the failure. And of course, the trench work and civil work has to be done by the contractor. And it will be under the supervision of our supervisor. Because post-padding and pre-padding is very important during the installation of the GRE pipe. For the underground and for the supporting is also important for the above ground application. So this way we can reduce and minimize the failure of the piping system.
If that piping system is designed, obviously the manufacturer has to endorse that, because if the manufacturer is not in agreement with the stresses in the piping system and the locations of the anchor block, he will manufacture the wrong pipe thicknesses and dimensions. So in fact, from the design point of view, the consultant should make a detailed stress design, take into account the surge and the water hammer. And then the manufacturer shall endorse it, and then in fact, in collaboration with the civil contractor who shall install it and the supervision, there should be a proper system. Of course, you need, with a composite pipeline system, you need more quality control. Standards have to be implemented very accurately, and supervision on site is essential, in fact, in particular if you have lamination of joints. If that is shortcut, you get all kinds of failures. Lamination of joints is something which needs to be carried out by very qualified people who are very familiar with the materials. And it is not easy.
There is no code and standard for GRP. And then the contractor, when he quote for that, then he quote for different material, for DI pipe, for MS pipe, but there is no mentioning non-metallic. Only polyethylene pipe, either HDPE or MDPE or whatever, because there are a design standard. Now, my question for Mr. Winston, what is required in order to have a more, worldwide known standard and codes for GRP in order to allow consultants also, to include GRP in their design for any system so that the other company could quote? Thank you.
Well, I'm looking forward to this ASME standard because, like I said, it's much more like B31.3. It's much more conventional. It's a standard stress analysis and product design development type of a strategy than, say, 14692. And I'm hoping that that will be helpful. I really think that the owner's specifications are crucial in deciding which of the standards we're going to consider and what part of those standards do we consider acceptable. Now, this is the manufacturer and his consultant is over here. The owner and whatever he does, he's the owner. He's the captain of the ship. He's going to determine how this comes out. And so in preparing specifications, he's got to be able to be insightful and put together a specification that selects the different documents that are going to be used and how they're going to be used in terms of product design, fabrication, assembly, both shop and field assembly, and installation. And he is probably going to need to get some help or something. He's got to, because he's in charge of this thing. The owner is the responsible party for quality. Always is, can't give it away. It's non-transferable responsibility. So he's got to be able to do it well. And certainly the specifications and documents that he's going to use as part of the contract is crucial. And then the enforcement of those through the design phase, through the fabrication, assembly, and installation phases is crucial, because ultimately his responsibility, if this is going to be quality and reliability is his responsibility. So he's got to be able to step up to the table, take responsibility, develop the documents, enforce and implement those documents, or nothing will ever get better. I mean, I've been following this for almost 50 years, and we've tried every gyration in the United States to make it better. And it got worse over the years, and what we found is the owner's engagement, meaningful engagement, got less and less and less, and we could directly track the frequency of failures getting more and more and more. As the owner became unengaged and was trying to transfer responsibilities to others that were untransferable. They're his innate, absolutely out of logic responsibilities. The more he handed them off, the worse it got. And we had a period there with ASME where we tried to identify the manufacturer as the problem. We're going to fix the manufacturer. The RTP1 certifications, shop certifications, all this stuff, it still got worse. So obviously the manufacturer wasn't the problem. And then in recent years, the owners have become much more engaged in a meaningful program by which they take responsibility to make sure the kinds of things that could lead to failures don't exist in their installed operating systems. Again, if you eliminate failure, what happens? You don't have failure, but who's the responsible party? The owner, the operator. If I own a boat or an airplane, I'm part owner in a couple of airplanes, it's my job to make sure it's flight worthy. I mean, nobody else, it's mine. Even if a mechanic works on it, it's my responsibility to make sure he's done it right. Same thing here. If we're going to hire a contractor and his fabricator and his consultant, it's good. Hire the right people, have good specifications, but we've got to be able to enforce those specifications to make sure the physical properties and the stress analysis means and methods are proper, and all the way through the shop. And once he takes ownership of that plant, that facility, then there's no question who's got responsibility. Well, he needs help there too with respect to preventive maintenance. If there's a problem, we want to stop it before it turns into a failure. But it's hard to do that on your own if your primary job is producing oil, petrochemicals, without getting some people whose primary function, core business, is risk management in reinforced plastic composites.
Manufacturers, they should have an association whereby they can approach these committees, like for instance, Pipeline Operating Forum. It's a committee looking after pipelines worldwide, you know, ASTM. And they approach these committees requesting to include the specification, to include this in their specification. So instead, you know, similar like for instance, the ASME, B31.3 or B31.8 or 4, whatever, they have a specification for metallic. They should have a specification for non-metallic so that the operating companies which are doing that, they can utilize these references, okay? Because the operator will not put an industry code of practice, will not. But we need the committees, international committees, who look after the development of standards to address that. And they will not move unless they receive a request from the non-metallic manufacturers and vendors. And this is the only way for those manufacturers to improve their business.
My name is Muhammad Soliman. I'm the manager of piping mechanical team in Zatco. Since the debate is for the non-metallic, the question is for Mr. Ornaldo, Mr. William, and Mr. Prakash. Experience for installation in your facility for the use of HDPE.
Okay.
Specifically, the successful installation and any failure incident.
where we have some problems, not in Habshan Complex, but in some other plants. HDPE was also highlighted as one option. HDPE is being considered for water systems in North America. So HDPE, it's being to start very popular in North America. There are some projects in Texas where HDPE in petrochemicals and refineries where HDPE was studied and was adopted. In Gasco, we did not do. We were just about to do a pilot test for HDPE, not in the water system, but in the hydrocarbon condensate. But it revealed that the original price cost for installation of HDPE compared with carbon steel was most probably 1.7 times more or almost 2 times more. So we did not go for that. I know that, for example, Shell DEP, they have the HDPE also certified and they adopt HDPE for certain services, one of them hydrocarbon service as well. But in Gasco, we did not apply yet.
I would like to thank you very much for your attendance, and I would like to thank the motion teams, the pros and cons. And please remember to fill in your format, feedback format, to be collected by DMS team. And I will leave the floor now to Rebecca for the closing.
Thank you, Mahmoud.
Thank you.
Thank you so much for all the input you gave us. It means a lot to us. We're going to break for lunch. Please feel free to join us. What we'll do about halfway, 1:30, we'll very informally announce the result of the vote, and we'll send you an email with a little update. And many thanks again. Many thanks to Composite Pipes, speakers, Mahmoud, and to us, of course. We look forward to the next time. Have a good lunch. Thank you.